If we hear the beep, it's good. All right, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you help us use this time wisely and help me not to get confused. Amen. All right, so question. Given, say, n vectors in V, let's say not n, let's say n k vectors in V, dimension of V equals to n, and let's say that beta equals to E1, E2, en basis for V, all right? So then beta star E upper 1, E upper 2, E upper n, dual basis. And we had EI, EJ, Kronecker delta IJ, all right? But anyway, suppose you're given k vectors, say V1, V2, Vk vectors in V. And you want to judge, are these linearly independent? Now that I write it out, I realize it's not quite what I wanted. I'm going to leave that up there. I'll come back to it when I'll come back to it. So this is section 4.1, which is on the algebra of alternating linear forms. And so, you know, we already stated the definition. What was the definition for definition? We have alpha is an element of what we call lambda sub k of V. What's that mean? Alpha is a mapping from what? From V cross V, how many times? K times, yeah. And we work with real valued forms, but you could put other stuff there. But by default, put the field over which you're working, which is reals for us. And what does it mean? This is not just any, so it's k-linear, which means it's linear in each entry, but also we have what? If we have alpha of like, you know, V1, Vi plus 1, Vk, well, that's equal to minus alpha of V1, Vi plus 1, comma, Vi. So anytime you flip pair of inputs, you get a minus for this alternating form, right? So it's a completely k-linear, completely alternating map. That's what these so-called k-forms on V are. K-forms on V, right? Or so theorem. And the first theorem we have is that if you have such an alpha, then number one, if we have alpha of V1, VV, VK, we get what? If you have any repeat, then if you think about it, then that's minus itself, right? So if something's equal to minus itself and we're working over the reals, that means it's 0. So this is 0. That's the proof. And then also, if you have alpha of V1, V2, Vk, Well, that's going to be equal to 0, given if, I'm sorry, let me, cart before horse. If v1, v2, vk is linearly dependent, then alpha of v1, v2, vk is equal to 0. So of course 1 is a very special kind of linear dependence, right? When you have one of them is literally the other one. But 2, actually any linear dependence amongst the entries will cause it to be 0. You have a question, Sam?
I was just trying to figure out the notation for number 1. Do you mean that v1 Are you multiplying?
Well, I guess I don't have to have, I mean, we could have v here. What I'm trying to say is that there's some repeated input.
Okay. So if there's any repeated input, no,
Just 2 of them. Yeah, it's 0. And that comes from this, I mean, if they have them adjacent, then you get it immediately. But if they're not adjacent, what's the rest of the proof? You just flip until they're adjacent, and then apply the definition. Yeah. Now, so this one, if they're linearly dependent, what's that mean? That means that you can find vk, which is equal to the sum, I equals 1 to, I equals 1 to k of ci vi, right? Well, I guess we could say k is a bad choice. Duh. Vj, I not equal to j. So like everything except for the jth one, right? It's linearly dependent over a field means that you can solve for one of the vectors in terms of the others, right? Not true over a module. But anyway, and so you just feed that. So without loss of generality, just suppose it's the first one, all right? Just to keep the combinatorial annoyingness down to a minimum. If you look at that, then alpha, you'd have alpha of v1 vk would be alpha of the sum, I not equal to j, k ci vi v2, and I'm sorry, I could be more specific here, right? I equals 2 to k given my choice of nomenclature. And by linearity, I can pull the sum out, I can pull the constant out, right? But then what do I have? I have I ranging from 2 to k. So the first entry in alpha it's repeated somewhere in that list. So by 1, it's 0. So alternating k forms are really good at picking up on linear dependence. So I think that's kind of an answer to the question I posed already. If I wanted to detect, right? If I wanted some sort of linear dependence detector, well, if I had an alternating k form, it seems like that might be something good to use, right? Because certainly if I have a set of vectors and I feed it to an alternating k form, then if those vectors are linearly dependent, then it's automatically 0. But don't get carried away. just because a particular k form gives you that its value on a set of k vectors is 0, doesn't force those vectors to be linearly dependent either. I'll show you that. So let's see your example. He says the determinant is an n form over V. And here's how he does it. We take the determinant of V1, V2, Vn. It's going to be the determinant, my notation, not his, of the coordinate vector of V1 with respect to the beta basis, the coordinate vector of V2 with respect to the beta basis, and so forth. Coordinate vector of Vn with respect to the beta basis. I'm still assuming that my basis for the vector space is beta, okay? And V is always going to be a finite, an n-dimensional finite vector space for this discussion we have here. Now, is that an alternating, if you flip any two columns, you get a minus, right? The determinant is linear in each column, in fact. This is true. You can prove it. And then, of course, the coordinate maps are also linear. So we get linearity in each slot. We get completely alternating. That's an n-linear form, or an n form over V. So that's one example. Of course, if V equals to Rn, then it's nicer, right? Because if V is equal to Rn, then we can just take the determinant of a bunch of vectors and we do what? We don't need coordinate maps then. We just do what? We just chuck it in to the corresponding matrix. You don't even need coordinate maps. You just concatenate them, take the determinant. That's an n-linear map. Example 2. Example 2, though, he says for I1, I2, ik in an element of 1, 2, n. So I have a name for this guy that, if you don't mind, I'm going to use in here. I like to call this thing the numbers, counting numbers up to n. I call this n sub n, typically. All right. And we also want 1 less than or equal to, well, I already got that. We want I1 less than I2 less than less than ik. So strictly increasing indices, right? All right. Strictly increasing indices. Then he defines, he calls it, he uses a, so I'm not going to use his notation. I'm going to modify his notation a little bit, guys. So, like, what's his notation in McNerney? Which is probably a mispronunciation of his name, but oh well. He uses epsilon 1, epsilon 2, epsilon n for these, but I will use the same letter with an upper index for the dual basis. So in similar fashion, he uses epsilon he uses epsilon lower I1, I2, ik here, but I will replace that with E upper I1, I2, ik. Or you know what? You know what I might even do? I might say that that's E upper I, where I is a multi-index. But anyway, this is going to be a mapping from V cross V cross cross V. How many times? K-fold times to the reals. And here's its definition. So what he does is he takes the determinant, right, the determinant of E1 V1, first column, E1, E2 rather, E2 V1, dot, 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 EK V1. Think about what we talked about last time. What that is those are the, oh, I did that wrong. Sorry, not so pretty. I1, I2, mind your indices, IK, sorry, yeah, like that. Those are the I1th, I2th, the IKth coordinates of V1. It's the selection of the K, those K particular coordinates of the V1 vector for the first column. And then he takes the same set of, like the same subset of coordinates for the second one. So this is actually the determinant. If you take I1, if you let the I expand to like the whole set of indices, then it's just the determinant again. But you see what we're doing. We're constructing a K by K matrix, right? Which means we can take the determinant of it, and since it's a determinant, well, it's completely anti-symmetric, it's multilinear, right? So this defines a exercise, right? But EI is an element of the K-forms over V, so constructed. So let me show you what I was talking about. Like I thought, well, maybe this is a way we can study linear dependence of vectors. It's kind of an interesting bit of linear algebra, right? So we could look at, let's see here, E12 of AB. We could look at E13 of AB. We can look at E23 of AB. All right. This is example 3. Now here I'm thinking A and B and R3. So this is the determinant of what? So we take the 1, 2 coordinates. You got your A1, you got your A2. You got your B1, you got your B2. You got your A1, you got your A3. You got your B1, you got your B3. A2, A3, B2, B3. So A1, B2 minus A2, B1. A1, B3 minus A3, B1. A2, B3 minus A3, B2. In fact, these 3 two-forms form a basis for the vector space lambda 2 R3. By the way. So my question is, do these detect linear dependence of the vectors A and B? In a vector space of dimension n, if we're given a full dimension set of vectors, it's easy to check for linear independence, right? Just shove them into a determinant. If the determinant's non-zero, they're linearly independent. If the determinant's 0, they're linearly dependent. Right? Feed them through the coordinate map. But when you have 2 vectors in a vector space of dimension 3, that's something we don't have like a hard calculational method for. Well, okay, fine, we do. It's row reduction. But how about an algebraic method, something that's formulaic? There's nothing like the determinant. ready off the shelf in standard linear algebra, but this is what this is. So can you tell me what the condition is I need to make A and B necessarily linearly independent?
All these y1, sorry, e1, 2, e1, 3, e2, 3, you apply those to the two vectors, and they all must be 0. Or they all must be.
Okay, so all 0 implies that A and B linearly dependent, right? However, on the other hand, if there exists even one non-zero, right? If you can find E, I, J, A, B not equal to 0, then that implies that A comma B is linearly independent.
So that makes the top one a high condition.
Yeah, right. That's also true. So another way to look at this, of course, is if we just take the two vectors, A1, A2, and A3, right? And B1, B2, and B3. What are we doing? Well, we're thinking about taking the determinant of submatrices, right? So in some sense, these wedge products have to do with they have some connection with determinants of submatrices, right? I can't take the determinant of a 3 by 2 matrix, but I can take determinants of 2 by 2 submatrices of it, and that's exactly what this does. Which is why it's not surprising you can prove things about determinants using wedge products, because it gives you an algebra which makes contact with the cofactor expansions and such. Anyway, let me get to the end of this here. So, theorem, if we look at the K forms over V, is a vector space with dimension. So what's the dimension of the K forms over V? It turns out it is n choose K, also known as n factorial divided by K factorial times n minus K factorial. So the basic point is that the dimension, the basic argument, here's a proof sketch. Your basis are things of the form EI, such that I is an element of the K indices taken from n sub n. So here I mean that this is E, I1, I2, da da da, IK in our current notation. And this is the set of all multi-indices of length K taken from n sub n, which there are n things in. So you can count. So what are we asking? If you think about setting up a index of length K, for your first choice, you have what? You got n choices for your first index, right? How about your second? There's no repeats, right? So then n minus 1, and you have to make you have to make how many K such choices? So that's n choose K. Which is that?
And each time, since it has to be strictly increasing, that's why it's actually better than permutation.
Yeah. All right. Then that brings us to the definition of the wedge product for a vector space. Where should I put it? Probably over here. So here's the definition. I don't think we need this anymore. So he defines the wedge product of the dual vectors. Here's how he does it. EI1 wedge EI2 wedge wedge EIK acting on V1 V2 VK is equal to the determinant of EI1V1 EIKV1 EI1V2 EIKV2 and so forth. So again, you're essentially just sampling subcoordinate vectors of your inputs. But here's the wrinkle. This is for V1, V2, VK in V, and 1 less than or equal to I1, watch this, comma, I2, comma, comma, IK less than or equal to N. I make no concession. I'm not saying that they have to be distinct or strictly increasing. We define the wedge product of dual vectors for any assortment of them, like so. All right. So this gives us a definition of the wedge product of the dual basis, your basic one forms. And then proposition, from this, you can prove, number one, that if we have EI1 wedge EI2 wedge wedge EIK, this is equal to 0 if any, I sub s is equal to I sub t in here somewhere. If there's any repeat, it wedges to 0. All right. And also, number 2, EI wedge EJ is minus EJ wedge EI. Oops.
So that's the same thing we defined there in the middle. So EI1, EI1 wedge, EI2, etc. is going to be the EI1, I2, IK that you find there.
Special case. See, because over there we make no assumption that they're distinct or increasing. So this would be, in fact, that's like the next proposition. Where's my proposition? Ah. Well, anyway, it is observation, let's call it. Maybe it's not even a proposition, but it's definitely an observation we can make, is that if I is an element of the multi-indices of length k over n sub n, or you could just say perhaps of n, that would suffice, yeah? Then n sub n is better. I can't make up my mind. Then I, in other words, EI1, I2, IK, is in fact equal to, yes, EI1 wedge, EI2 wedge, wedge, EIK. Yes, that is true. The thing is, the multi-index notation for E, he's reserving for distinct and increasing indices, apparently, as far as I can tell. All right, great. So let's move on. I don't want to spend all of class on this one. So what we're trying to do right now is I'm just trying to show you how we can actually concretely build up the wedge product from determinants for a finite dimensional vector space. It's not actually that hard. That's what we're doing, right? We almost are almost there. So how do you, so now we've got the wedge product on dual vectors. We'd like to define the wedge product on what? What's next? This just shows us how to wedge together basic one forms, right? We need to talk about how do you take the wedge product of What? Yeah, like about a K form and a. There's a typo in the book here, unfortunately. So this is definition of wedge product. So we have alpha is the sum I1 less than dot 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 less than IK. And I'm going to use the notation alpha lower I1 dot 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 IK. And then E I1. And so here's his, I don't know, like, I mean, I'm just going to do it like it should be done. I'm just going to put the wedges in here. Fine. He drops the wedges for these. And that's okay. It's just a shorthand for him. That's fine. I'm going to do it this way. So sum J1 less than J sub L. He says beta is a 1 form in the book. That's a typo. Because he apparently means it's an L form if you read everything past that point. All right, so what's the definition of alpha wedge beta? He says it's exactly just the sum. Let's say, so I could, it's kind of nice to rewrite this way. This is the sum over I, alpha I, EI, and this is the sum over J of beta J, EJ. Of course, this is in the K forms over V. This is in the L forms over V. And so, in short, it's just the sum over ij of alpha I, beta j, ei, wedge ej. That's the definition. Now, to be more explicit, that's I1 less than I2 less than da 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 less than IK, J1 less than J2 less than da 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 less than JL of alpha sub I1, I2 da 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 IK, beta sub J1, J2 da 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 JK, E I1 wedge E I2 wedge da 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 wedge E IK, wedge EJ1 wedge EJ2 wedge da 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 wedge EJK. There you go. Now that's not written in terms of the basis forms. So this definition is not given in terms of the basis. I mean, this is, it's, well, it's not, I guess it's not entirely clear. There's an exercise here to show that this is in fact a K plus L form over V. All right? Claim. Some of those things are 0. Because in principle, you can have repeated dual basis elements in the alpha and the beta. All right? Yes?
Should the sub-indices on the J's be L, or do they?
Oh, I'm sorry. That was supposed to be an L. Let me fix it. All right. So I'm pretty pleased with this. This gives an actual pretty explicit construction of the wedge product. That's, I'm sure it's got a gap in there somewhere, because I remember it being more awful than this. So he's got these exercises, prove this and that. Somewhere in those exercises is something horrible. So I'm going to assign them to you, and you'll find out where. What? That's what students are for, right? Here, let's look at an example. Yeah. Well, yeah, we're that's also an exercise. Let's see here. Actually, I'm not sure. An example here is terrible. I'll do an example. What example? Where am I? What example did I get to? Is this 4, 5? I forget. 4. So he has this one. It's a good one. He says, uh-oh, I lost Travis. You here? Okay. He says like W is, let's say, E1 wedge E2 plus E3 wedge E4. And now he writes it in the 1, 2, 3, 4 notation. I'm going to write it like this, though. And so if we calculate omega wedge omega, if you get carried away with what I erased here, you get to thinking, well, the wedge product of any form with itself is 0, but that's just not the case. If you have a 2-form wedge, a 2-form, it doesn't have to be 0. It can be something else. So like this, we can work it out. So, you know, what this definition says, guys, is just that you pretty much take the wedge product just like you take other products. You distribute, you keep things in order, and you mind the anti-commutativity of things as appropriate, you know. So if you're calculating, you know, product of dot product with the product across the dot product, then, you know, you got commutativity, right? If you take product across a cross product, then you got the anti-commutativity. If you take the product across a matrix product, then you don't even have either. I mean, it's just generally non-commutative. And so this is not exactly non-commutative, but it's kind of partly commutative in some regard, right? So anyway, E1, wedge E2, wedge E1, wedge E2. Actually, you know what? If you don't mind, I'm going to not write that down. So when we take the wedge product of this and this, since there's a repeated E1 and a repeated E2, that's 0. Right? When I take the wedge product of this and this, I get an E3 repeated, so that works out to 0. So the only thing I have to really worry about is E1, wedge E2, wedge E3, wedge E4, plus E3, wedge E4, wedge E1, wedge E2, wedgie, which you can collect into one term. Right? This is 2 times E1, wedge E2, wedge E3, wedge E4. See, I can, did you guys get that? This one here, I move it 1 and then 2 spots over to there, right? And then to this one, likewise, 2 spots over. So I can get from here to there using 4 swaps, which is a net of plus. So there you go. The wedge product of this particular 2 form is that 4 form. And this calculation makes sense for any vector space of dimension 4 or higher. Yeah. All right. But yeah, the now I feel like I'm starting to get into reruns at this point. Proposition. If you have alpha and beta in the dual vectors, right, and you got v and w are in v, then we have a few things. Number one, you can calculate alpha wedge beta acting on VW. This is the determinant of alpha of v, beta of v, alpha a w, beta a w. All right. So I mean, that's a claim. It's not, that's something you could work out from the definitions that we've given. But suppose you had. How would that relate to other things we've said? Check it out. So this is alpha of V, beta of W, minus alpha of W, beta of V, alpha of W. These are real numbers, right? So you could look at it as this. This is actually alpha tensor beta minus beta tensor alpha acting on VW using the tensor that I introduced last time. So this is consistent with what I claimed last time, which was that the wedge product is the antisymmetrized tensor product, right? So this holds for arbitrary VW. So you can see from this that alpha wedge beta is nothing more than alpha tensor beta minus beta tensor alpha. If you want to link back to the tensor product of one forms, you could do that. That's a close cousin to part 1 of proposition 4.27. Number 2, alpha wedge alpha, 0. Number 3, alpha wedge beta is equal to minus beta wedge alpha. These things have not been said before today. You notice what I said before was that the wedge product of a dual basis with itself was 0, and that they were antisymmetric. Now I'm making the comment for arbitrary covectors, right? So it's not the same as what we said earlier. But actually, once you have this formula, these two things are immediate, right? Because alpha wedge alpha is a 2 form. So if it's 0 on all possible inputs, that means it's the 0-2 form. But it's pretty clear that if you put alpha and alpha into this formula, that determinant's 0, right? And once you know this, it's easy to prove that. So how do you do that? I think if we take alpha plus beta, wedge alpha plus beta, what's that give us? Well, that's 0, right? By 2. So this is what? This is alpha wedge alpha plus beta wedge alpha plus alpha wedge beta plus beta wedge beta equal to 0. But these two things are 0, so those things have to be negative. So in that sense, 3 follows from 2, given the distributivity properties. The fact that the wedge product is distributive is I'm not even going to write it out, guys, because look, I've shown you enough. I think I'm going to stop. I'm getting bored. Where was that thing? I was at least going to tell you the number. Stupid thing, go. I wrote it down here. I did. Proposition 4.2.15. Oh, I guess it's probably bad to use that here, huh? But if you look at proposition 4.2.15, this has the, oh, no, that's not the one. That's something else entirely. Ah! Goodness gracious. That's a stupid thing, go. 4.2.8 is what I was looking for, which is the one after this. Oh, well. So I still lose, but goodness, if we had this, it would be really easy to prove that. Wait, you can prove these things natively just from this formula, I think is the point of this proposition. 4.28 actually says that the wedge product is distributive, it's associative, and it obeys the graded commutivity that I wrote down last time. Okay, so please read this part of McNerney. He also develops 2 more things in the section on pure linear algebra. He talks about the pullback of a form with respect to a linear transformation, and he also talks about the so-called interior product. So the pullback is a way to take a form on W to a form on V if you've got a linear transformation going from V to W. And then this interior product is a way of taking a k form and reducing it to a k minus 1 form by just evaluating at a given vector. Okay, so it's a contraction. And I could talk about those right now, but I think that's kind of vain. We should wait and talk more about those when we actually do the differential geometry corresponding thing. So I'm going to save that algebra for when we actually use those, when we use it on, like, you know, differential forms and such, all right? But it's good if you read it now. It's very clean and nice and neat. I think this section is really well written. And I'm happy we did this. I think this is healthy and good to have constructed the wedge product like we have. And after you do the homework to fill out the gaps, you'll understand why it's an incomplete discussion. No? Sam doesn't look too happy about it. Oh, think about something else. All right. Okay, so let's get back to the fun stuff. Yes, differential forms. So, how can I make these into differential forms? I want to make this into a differential form over a manifold. What do I do? This expression is ill-advised. All right, so dx, 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 dx. So we can use all this handy-dandy multi-index notation for differential forms. We suppress the point because it gets really old. So, I mean, technically, this is the wedge product of two differential form fields. The alpha sub I and the beta sub j are now functions, right? He actually is very clear on it. He's like, what is alpha wedge beta? How do you define that? He said, well, that's alpha of p, wedge beta of p. This is in McNerney. And he's like, basically, we define the algebra of differential forms, form fields, if you will, point-wise by the wedge product we talked about here today on a vector space. So you just point-wise do the algebra that we've been developing today. It's just like calculus 3. We build on how to like add vectors and scalar multiply vectors. Then we talk about vector fields. How do we add and scalar multiply vector fields? Point-wise in the same way. So the same thing's going on here. We develop an algebra for forms at a point, and then we can do the same algebra on form fields by point-wise applying the wedge products. All right, so there's that, which is not especially exciting, but it's kind of important. It's the backdrop. So suppose you want to calculate, then we started doing some things like we calculated the exterior derivative of one form, a two form, a zero form, an R3, right? So what's the definition for the exterior derivative of alpha? Here's the slickest notation I know for it. Sum over I of d alpha I wedge dxi. So I could even put some, I won't be stingy, I'll put in some parentheses for you. There you go. The d alpha I, that's the total derivative of a function, right? We're mostly going to be thinking about differential forms on Rn, all right? So, I mean, to be more pedantic about this, this is the sum over j, the sum over I1 less than I2 less than Ik of partial alpha I1, I2, dot, 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 Ik, partial xj, d dxj wedge dxi1 wedge dot 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 wedge dxik. So all that formula says is you take the total derivative, total differential of the component functions, and you wedge it with the wedges which are already there. In the context of a manifold, you can prove that this is a coordinate-independent construction despite the apparent dependence on coordinates. I won't do that. But you can prove other things, right? Like we can calculate what's the exterior derivative of a wedge product. What would happen if we calculate the exterior derivative of alpha wedge beta? Right? So let's see here, where should I do it? I think I'm going to erase this mess up here. I will regret that. Let me prove it over here. So exterior derivative of a alpha wedge beta. And let's suppose that this is a K form and that this is an L form, keeping with my lingo so far. This is going to be I mean, you can calculate that that is, let's see here, you know, there's something that makes life a little bit easier here in terms of something I should mention. Something I should mention. Oh, lost my X's. But usually I'm thinking M equals to Rn, you know, at the moment. Well, that's not necessary, though, right? I mean, we talk about the covectors to a, we talked about the cotangent space to a manifold, right? So we could build up. I have laid the groundwork to talk about differential forms on a manifold here just the same. Not carefully, but at least a little bit. So suppose you don't, I mean, this kind of summation is really kind of a drag. Like this. So I want to just, before I get into this proof, because it'll make my life a little bit easier and not drag me kicking and screaming into certain combinatorial questions. If I write alpha as the sum over I1 less than da 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 less than IK of alpha I1, you know, through IK, and then dx I1 wedge dxik. Well, you know what? I can also rewrite this as the sum over I1, I2, da 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 ik equals to 1 to n. Supposing we're working in an n-dimensional context here, guys. And so something goes in the front here. I1, I2, da 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 ik dx I1 wedge da 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 wedge dx ik. And here's where it pays off that he defined the wedge product not just for increasing indices, but for possibly repeated indices. Do you see the difference between these sums? Here, I'm looking at increasing indices. And this is just over all values. 1 to n, you know? Let's work out a small one, all right? How about if we've got, but if we just got look at like a 2 form. Suppose I've got alpha is the sum over you know, I less than j. All right? And we're looking at alpha ij dxi wedge dxj. And I want to rewrite this as the sum over alpha ij dxi wedge dxj I comma j. Just free from 1 to n. Right. We need to make an agreement that we define like alpha 1, 1 and alpha 2, 2 and so forth and so on. These are understood to be 0 in this case. Because technically speaking, you really would only define the alpha ij with respect to the basis of the two forms, which would just be over the increasing indices. And yet, I want to write this formula, which is not over a basis, which is over all possible wedges. So this, what is this? We can break this up. This is actually the sum over what? I less than j, alpha ij. I feel like I'm doing one of your homework problems, but you'll forgive me for doing that. dxj. You're like, you haven't announced the homework problems yet, so no harm, no foul. Very, very true. I greater than j, alpha ij. I mean, them's your cases, right? Why? What about the third case? What's the third case? The third case would be I equals to j, right? If you're looking at a pair of two indices, I and j, you either got one less than the other's less than the one, or they're equal. If they're equal, well, that's 0. Now, we also have to agree that, so this would actually, we also need another definition, which is that alpha ij is equal to minus alpha ji. We must insist on that. So, in other words, you know, I would have an alpha 1, 2 in the natural basis decomposition for a 2 form, but I'm saying I also have an alpha 2, 1, and it's equal to minus alpha 1, 2. This is the notation we want to use. So, with that, what can I do? I can relabel this, right? I can say what this is really the sum over, let's say, all right, let's get nuts. I less than j. I don't usually do that, but alpha ji, right? dxj wedge dxi. What's that? Well, all right, but this can be rewritten as what? I less than j minus alpha ij, right? Flip these, dxi wedge dxj. In other words, this is that. So we get 2 times.
Negative dxi wedge dxj. Negatives on the bottom.
There's 2. Yeah, did I not? I'm sorry. Thank you, Travis. I meant to write minus there, but I just wrote it in my mind, which doesn't count. It's here.
Only we can say that.
Well, you can. I just don't care. Sorry. I'm a monster. So if you look at, I need to watch Arrested Development again. See here. This equals to that tells you the formula we're looking for is that apparently this is equal to half the sum over all indices.
So there should be 1/2 of
No. In fact,